Section 1.8, combinations of functions and composite functions. So what we want to do here is we want to look at functions as quantifiable amounts. There are numbers, there are letters, there are different operations, but really a function is quantifiable. You can measure it depending on what you define your x value as. You can define it numerically. If you don't define what your x value is and you leave it as a variable, you can still quantify it with like terms. So numbers, letters to certain powers. So combinations of functions are the four operations. You can add, subtract, multiply, and divide. It just depends what your function rules are. So we have f of x being 2x minus 3. We have g of x being x squared minus 1. So if we wanted to add f and g together, what we're going to do is we're going to take those two function rules. We're going to take 2x minus 3. We're going to take x squared minus 1. And we're going to add those together, combining any like terms where we can. So we have x squared, we have 2x, and we have negative 3 and negative 1, giving us a negative 4. With subtraction, just be careful. Make sure you're subtracting every term. You're distributing that negative. With multiplication, you're going to want to probably do some foiling and distribution. You want to be careful and stay organized. With division, this might actually be the easiest one to do, because when you take a linear and you divide it by a quadratic, yes, you can do that division, but usually the result is a lot more gross and unsatisfying than what you started with. So a lot of times with division, if there isn't really an easy path forward, you just leave it as it is. So that's combinations of functions. The other part here is composite functions. Really, for some unknown reason, this is like one of my favorite things in algebra. I don't know what it is about composite functions, but it just makes me so happy and joyful to look at them. So, composite functions are where one function actually becomes the input of another. So functions get plugged into each other. You can do this once, you can do it twice, you can do it numerous times. You can define what the x value is and evaluate, or you can leave the x value undefined and you will have x in your answer. So composite functions, this is a little blurry, let me spell it out a little more. It's f of g. I remember when I was in high school, I thought, oh, fog, which has nothing to do with composite functions. It's just what I thought when I was 16 years old. However, I don't really like this notation the most. What I do like is this. You read both of these the same way, f of g of x. But over here, I think it's a little more clear that g of x is the input for your function rule f. So g is literally being plugged into f. So if we look at composite functions, f of g of x, so we have f, which is x plus 2. We have g, which is 4 minus x squared. Now it's very important here that you realize what these functions are talking about. When you say f of x, just the function, f of x, x is being plugged in. What comes after of is being plugged in. So f of x gets plugged in. F of 2 gets plugged in. So when you have f of g, that means that f of g is getting plugged into the f function. So 4 minus x squared, that is getting plugged in wherever you see an x. It could be one time, it could be multiple times. Wherever you see that x, you plug it in. Just like when you're evaluating functions. When you do f of 2, you plug 2 in wherever there's an x value. F of g, you plug g in wherever there's an x value. So, the rule for f of x is x plus 2. You take whatever your input is, you add 2. Well, now our input is a function. So, 4 minus x squared. So you look at adding these together. So, well, not adding, sorry, composite functions, composing these, g getting plugged into f, and then you combine like terms as best you can. So we have a negative x squared, and we have 4 plus 2 to give us 6. So the order matters, f of g or g of f. Here you're going to be reversing it. F is going to plug into g. And the last little bit we have here, this is kind of cool, a little bit of reverse engineering here. You start with h of x. Start with a composite function. The quantity, 3x minus 5 to the third, plus 1. So you think to yourself, okay, what got plugged in to this problem? If we look at this expression here, what got plugged in? Okay, so you want to think to yourself, kind of pull this apart. What's the overall function? What got plugged into that overall function? You kind of pick those pieces apart to get an f and g when composed, give you the function rule for h.